Welcome to lecture number 26 of the course Quantum Mechanics and Molecular Spectroscopy. Okay. We will have a quick recap of the previous lecture before proceeding. In the last lecture, we looked at the total Hamiltonian H is divided in two parts, which is H nuclear and H electronic. Okay. And the H electronic will consist of terms Ke of electrons, potential energy of electrons and nuclei, and potential energy of nuclear repulsion and potential energy of electron repulsion. All this put together, one call it as a U relative, okay, and the energy that comes out of this, and this the H nuclear will consist of Ke of nuclei. Okay. Now that means your H internal, that is the motion of the nuclei, can be written as Hn plus U relative. And I told you, for a given nuclear configuration, U relative is equal to constant. And we can always measure energies with respect to some constant, that is U relative. Therefore, one can treat U relative is equal to 0, that means measurement of energies relative to U. Okay. So, what you get is H nuclear is equal to H internal. Okay. Now, if you had two atoms A and B, separated by a distance r naught, okay, and which is fixed. So, which means the AB nuclear configuration is rigid. So, AB nuclear configuration is rigid. That means A and B are not moving with respect to each other. In such scenario, the kinetic energy of AB, which is nothing but minus h bar square by 2m A del square A minus h bar square by 2m B del square B, can be written as minus h bar square by 2 capital M del square Cm minus h bar square by 2 mu del square internal. Okay. Now, what is in where M is equal to MA plus MB and mu is equal to MA MB divided by MA plus MB. This is the total mass, this is the reduced mass. okay. And this is called, this transformation is called center of mass transformation. Okay. So, one can think of it like this, if you have an axis, okay, A, B, and distance is R A, this is R B, you can have center of mass somewhere here, which I will call as R center of mass, and then there is a R naught, which is the distance between A and B. If the coordinates of A are x A, y A, z A, and coordinates of B are x B, y B, z B, then one can tell R naught is equal to square root of x A minus x B whole square plus y A minus y B whole square plus z A minus z B whole square. This I will also write it as x square plus y square plus z square square root of, where x is equal to x A minus x B, y is equal to y A minus y B, z is equal to z A minus z B. Okay. So, what you have, your Hamiltonian H will now be equal to, or the nuclear Hamiltonian will now be equal to minus h bar square by 2 capital M del square center of mass minus h bar square by 2 mu del square internal. Okay. Now, this is nothing but motion of center of mass. What is the motion of center of mass? Motion of center of mass simply means that the whole object AB is moving in some direction, and that will not contribute to the internal structure. Okay. Therefore, one can write minus h bar square by 2m del square Cm, if this multiplied by chi n is equal to E n chi n. Okay. This is free particle. Okay, because it has no potential energy term. So, this is a free particle. So, when you have free particle, your energy is E n is equal to h square k square by 2m. Okay. And we know this E n is the not quantized. So, the energy of the free particle of course is not quantized. Okay. So, that corresponds to the translation. So, this essentially corresponds to translation energy of the AB molecule. Okay. Now, one need to deal with this, your H internal will now be minus h bar square by 2 mu del square internal. So, that will be nothing but minus h bar square by 2 mu d square by dx square plus d square by dy square plus d square by dz square. So, this is the Hamiltonian that we need to solve. So, the corresponding Schrodinger equation would be minus h bar square by 2 mu del square internal, okay, into some wave function, I will call it as a phi, is equal to E phi minus h bar square by 2 mu d square by dx square plus d square by dy square plus d square by dz square, whole thing acting on phi is equal to. So, this is the equation that we need to solve, Schrodinger equation. Okay. Now, to solve this Schrodinger equation, we have to look at one important point. Okay, that is the following, is that if you have A B, okay, and this is say called, I'll write it as R, capital R, okay, and of course this can rotate in the plane of this board and also perpendicular to plane of this board. Okay. So essentially what we are looking at is that without changing the center of mass remains fixed without changing the center of mass. Okay. Now that means we have a rotating particle, a particle that can rotate in xyz directions. Okay. So now your del square internal was nothing but in Cartesian coordinates d square by dx square plus d square by dy square plus d square by dz square. Now, but we have only the center of mass is fixed. So, we have only the rotating particle. So, we can transform this into spherical polar coordinates. So, we do another coordinate transformation. Wherein the del square internal can be written as d square by dr square plus 2 times by r d by dr minus L square by r square h bar square. Okay. So, this is the transformation in spherical polar coordinates where I will come back to what L is. So, your del square internal will be d square by dr square plus 2 by r d by dr minus L square by r square h bar square. Okay. And where your L square operator, okay, is given by minus h bar square into 1 over sin theta d by d theta sin theta d by d theta plus 1 by sin square theta d square by d phi square. Okay. Now, let me tell what these terms are. Okay. Now, we had the Cartesian coordinates x, y, z to begin with. So, let us suppose you have a Cartesian coordinates x, y, z. So, there is a point here which is represented by x, y and z. Okay. So, I will call it as this as a z axis and this is x and this is y. Okay. Now, this distance is r, okay, and this angle along z axis is theta, okay, and the projection of this onto the xy plane, okay, is the angle phi. Okay. So, that is how you define x, y, r theta and phi. Okay. So, initially you had x, y, z, okay, there are 3 independent coordinates that describe this point. Now, you have similarly 3 independent points, that is r, theta and phi, 3 independent variables. So, essentially you are going from one coordinate to the other coordinate. Okay. Now, your del square internal, okay, your del square internal will be nothing but, okay, if you ignore r, okay, if I fix r, okay, if r is fixed, if r is fixed, why am I fixing r? I am fixing r because I am considering that the molecule AB has a fixed radius, r naught or capital R, does not matter. Okay. If r is fixed, then of course its derivatives will you cannot have a derivative with respect to a constant, okay. You can only have a derivative with respect to a variable. So, you can ignore these two terms, okay. Then all you are left out with this. So, that will be equal to minus L square by r square h bar square, or this I will call it as a rotational Hamiltonian, H rotational under rigid rotor approximation. Okay. So, my H rod now will be equal to L square by internal r square h bar square, okay, into so this is into this minus into minus this is your del square. So, h bar square by 2 mu. Okay. So, when I rearrange this will be this h bar square, this will cancel, negative sign will also cancel. So, what I am getting is L square by 2 mu r square is going to be h rod. Okay. Now, this is written as L square by 2 I e, where I e is equal to mu r square, and this is called moment of inertia. Okay. So, at the end what I have is my H rotational is equal to L square by 2 mu r e square. Okay. Why am I writing r e or r? Because I want looking at the equilibrium distance. So, A, B, this distance is I will call it as r e, equilibrium distance between the two A and B, and it is not changing, it is a rigid rotor approximation. That means A and B are fixed at one place. So, this is nothing but L square by 2 I. Okay. Now, what is my L square? L square is equal to minus h bar square into 1 over sin theta d by d theta sin theta d by d theta plus 1 over sin square theta d square by d phi square. Okay. And one can quickly look at, this is nothing but your angular part of H hydrogen atom, or this is also nothing but particle on a sphere. Okay. And the solutions of these are given by solutions of these are given by what I will call a y, okay, j m theta phi. These are called spherical harmonics. You can look up any elementary quantum chemistry textbook or quantum mechanics textbooks to look at the spherical harmonics. Okay. Now, in spherical harmonics you have two important notions. One is the total angular momentum, given by L square operator, and there is a z component of angular momentum, which is given by Lz. Okay. Now, we know that your L square operator is your YLM is a eigenfunction of the L square operator, h bar square into j plus 1 into yjm theta and phi, and your Lz operator acting on yjm theta and phi will give you m h bar yjm theta and phi. Okay. Now, let me quickly write once more. Okay. So, essentially your yjm theta and phi are eigenfunctions of the operator L square, which will give you eigenvalue of h bar square into j plus 1 yjm theta and phi, and other is Lz operator is also has eigenfunction of yjm theta and phi, which will give you m h bar yjm theta and phi. Now, there is one important thing you must realize, that if there are two operators have common eigenfunctions, then the operators must commute with respect to each other. So, which means the commutator L square Lz must be equal to 0. So, operators L square and Lz commute with each other. Okay. Now, let us go back to our Hamiltonian. Your H rotation was nothing but operator L square by 2 mu R e, or same as L square by 2 I e. Now, you can see 2 mu R e, or this part or this spark, is just a constant. So, if you multiply a constant, okay, the wave function is not going to change. So, we have this Hamiltonian, and because this Hamiltonian consists of the operator L square, okay. So, this Hamiltonian will have same eigenfunctions of L square, okay, except that now they will be multiplied by different constants. So, you have H rotational acting on yjm theta and phi will give you h bar square divided by 2 mu R e j into j plus 1 yjm theta and phi, and this is your eigenvalue. Therefore, your Ej, okay, now we have a that is rotation with the quantum number j will be equal to h bar square by 2 mu R e j into j plus 1, which is same as h bar square by 2 I e j into j plus 1. Somehow this is written as h b j into j plus 1. Okay. Therefore, if I write like this, okay, now what I have got h bar square is h square divided by 8 pi square IE, okay, j into j plus 1. Now, if I remove h, then I am left with so instead of h square I can write h into 8 pi square. So, if I take this as BE, then I will get this one. So, your BE is equal to h by 8 pi square IE. E rotation, that will depend on value j, will be equal to h bar square by 2 IE j into j plus 1. This is also equal to h BE j into j plus 1, where BE is equal to h by 8 pi square IE and has a unit of second inverse, because you see energy is joules and h is joule second and j's are just quantum number. So, this must be joule second. So, has to be multiplied by second inverse, okay, and so this should give me joules. Okay. So, BE has a units of second inverse. So, if you finally what you have? We have the following: your h yjm theta and phi, or h rotation, okay, is equal to E rotation j yjm theta and phi, and your E rotation j is given by h BE j into j plus 1. So, this is your energy and this is your wave function. Okay. So, we can now look at transition. Okay, now they are quantum numbers. So, you will have rotational states that are j is equal to 0, j is equal to 1, j is equal to 2, etc. Okay, and we can look at the transitions between these in the next lecture. I am going to stop it here. Thank you.